We are with the start with thermodynamics, thermal heat, dynamics, moving. So we have a heating curve here where there'll be some other videos where we go into that in more depth. If you look at it, you can see the y-axis is temperature. This one is in degrees Celsius. We're going through all the phases here. So we're typically using Celsius for thermodynamics. And on the x-axis is the amount of heat added. You'll notice that there's not actually any numbers on this one. It's just showing the progression as we add heat, what happens. So you'll often see that. Sometimes you'll have numbers, but most of the time you will not. And then we have the items on the left side. Notice the flat area is where we are changing phases. So the bottom phase change is the melting point, and the top phase change is the boiling point. What you can remember for these phase diagrams is a solid is always what you're going to see at the bottom, because that's when it's at its coldest. And then it melts, and then it's a liquid, and then it melts, and then it evaporates or boils, and then it is a gas. Okay, some interesting things here. When you are in a phase change, the temperature is not increasing because we're taking all that energy inside to have the state change. So we're starting off with a liquid here. We're still going to have some liquid and some gas going, but all of that energy is going internally, endothermically, so that we can have the phase change. And at the end of the phase change, then we can start heating up the gas again. And that's going to happen at each point. You're always going to have two phases on those flat lines. Now, this temperature, what is it measuring? It's actually measuring the kinetic energy. So that solid is vibrating in place. It's not moving very much. The liquid is flowing, moving a little bit more, and the gas is random all over. So as we increase the temperature, that means we have more kinetic energy. Yeah. And this is a direct relationship. As we add more heat, we are going to do increase the temperature of the state until it makes it to a phase change. Okay, so we talked about endothermically, pulling that heat inside to change the temperature, or to not change the temperature, to change the phase. Okay, endothermic is a positive change of heat, and exothermic is a negative. So when we have exothermic, we would be going the other direction on the graph. If we have a gas, we have to lose heat, or the heat has to exit the gas to become a liquid, because that liquid does not have as much kinetic energy. Okay, if you want, relate all this back to ice, because that makes it kind of easier to remember. The solid is the coldest, so it has the least heat. So to get to a solid, we had to exit our heat. Exothermic is a negative change in enthalpy. So you're always going to have some change in heat or change in enthalpy. Just depends on which direction you are going. So again, this is the heating curve, solid, liquids, and gases. And we have some equations that we've been using. The MCAT, MC delta T, we just call it MCAT for easiness, but it's mass times the specific heat times the change in temperature. And that is the MCAT equation, or the N delta H equation. Okay, N, number of moles, times the change in enthalpy. So which equation can we use where? We are not changing the temperature when we're on our blue lines. So we can't use this one, because that is going to tell us that the heat is zero. We know the change in temperature and change in kinetic energy is zero, but the actual heat of what's going on is still occurring and can be measured. So the flat areas get measured by the moles times the delta H. And most of the time they're going to give you the delta H. Just note that there's a different delta H if it's a solid, liquid, gas, or whatever phase change it's in. So they could give you the delta H for vaporization And then that is what you would use up here for the phase change of vaporization, for example. Right, so let's do a problem. Determine the total heat of 2 moles of water that has a 10-degree temperature change. You got to figure out which equation. Q equals mc delta T. Q, which is heat, equals N delta H. Now, just because you see moles here does not automatically mean that it's going to be this equation. We have to figure out, is this a phase change or a heating of something? Determine the total heat of water that has a 10-degree temperature change. Okay, so that's not a lot of information, right? That's really, really vague, and they did not tell us if this is a solid, liquid, or gas. But typically, if you see it, just say water, that would be liquid water. So if you don't have any other information, you can write up there, assume liquid. Okay, hopefully most of the time they will tell you that. All right, so we have liquid water. We know liquid water has a specific heat of 4.184. Okay, now it does not say we're going through a phase change, just a temperature change, and they did not give us a delta H. If they do not tell us what the phase change is, we cannot get a delta H. It's just not physically possible unless they gave us the total heat too. So there's some couple indications there that we cannot use that equation. So we're going to use this guy. And we need to find the Q. So we need the M, the C, the delta T. We had a change in temperature, 10 dots. Again, we had a temperature change there. So as long as that temperature change did not involve a phase change, like it's not from 95 to 105, we are good just using the MCAT. In higher years, you might have to use both to add up to get your total heat. And our M, I don't have our M. Okay, that is mass in grams. But what do I have? I have 2.0 moles of water, and I want to convert it from moles to grams. Whenever we have to go from moles to grams, the 1 always goes with the moles, and the molar mass always goes with the grams. There's 2 H's and 1 O in water, hydrogen 1.01, oxygen 16.00. So there's 18.02 grams per every 1 mole of water. So 36.04 is our mass right there. Okay, so if you're following along and checking your work, those are the equations that you would have. And what we get there, 1506.24, is that our answer? Substitute, solve, sig figs. So 1, 2, 3, 4 sig figs here, because if you see the decimal, trailing zeros or zeros on the right are important. 1, 2, 3, 4 for the specific heat, and that's actually 10 dot. Okay, so this is still a trailing zero, even though it's to the left of the decimal. The decimal place only matters if you see it or you don't see it. Doesn't matter where it's at. This is still a right zero, so these guys count. So we're going to round to 2 sig figs. So underline the first 2 sig figs. The next guy is a 0. So 1500 joules would be my answer. Now, when you do the SOL, you might get something like this for your statements here. And you have to walk through. Don't just automatically put in what the calculator said, because we know that's not true for sig figs. Okay. And so 1500. I don't have a 1500. Does that mean I just pick 1506? Let's go back. That has 1, 2, 3, 4. So that is not going to be correct either. Okay, 2000, that would be if we only had 1 sig fig. So if it was 10 and not 10 dot, you would pick 2000. So I'm now between these two. Exponents are positive, which means we're making bigger numbers. So our hops are going to go to the right. 1.5 with 3 hops. 1, 2, 3. That's 1500. Both of these guys are 1500. Oh, sig figs. 2 sig figs in this one. 3 sig figs in that one, because you don't count the sig figs after the X. Okay, so our answer in this case would be B. Notice you didn't even have to do the problem on this one because these are all the same number rounded to a different number of sig figs. So sometimes they do that for you as well. This guy is what you would do in the lab if you were doing a calorimetry experiment. Oftentimes it is, yes, just 2 coffee cups in there with a thermometer, and then you could put a chemical reaction in here, or you could just put ice melting, whatever you wanted to measure depending on what's going on. If you have a chemical reaction going on, or you put a piece of metal in there and see how it cools off, a heated piece of metal, then your calculations get a little bit higher, but we're not going to focus on that on this video. But I did want you to see what an apparatus looks like in case you do see it on the SOL. Okay, so you have 2 different things that can happen. And when we're looking at these and we're looking at the temperature increase, that's not the temperature of what's happening inside the molecules. That's what's happening to the surroundings. Okay, so if we see this temperature increase, it means we had a little tiny chemical reaction that released heat. So if you see a temperature increase, we released heat. It is exothermic. Okay, all that little energy in every molecule went out into that surrounding solution area. Okay, what happens if you see the temperature decrease then? That means that heat from the surroundings got sucked inside the molecules, endothermic. So just remember, exothermic is negative, endothermic is positive, and we know this by the delta H. So if you calculate the delta H as negative, it's exothermic. If you see the temperature increase, it is exothermic. That heat exited on that calorimeter. What if they give you this thing here with some little diagrams of the structures? Okay, first you got to be able to identify the structures. A, vibrating in place, it's the coldest thing, so this is a solid. This guy, filling to fit the container, liquid, moving a little bit more kinetic energy, and gas. Gas has the highest kinetic energy. Okay, and where are we going? We're going from flask C to flask A. Okay, they didn't talk about flask B, so we are skipping flask C. So this is not a gas condensing into a liquid and then a liquid freezing into a solid. It's going directly from a gas to a solid, which is deposition. Okay? And so deposition, what is happening? Is that endo or exo? The solid, is that cold or hot? The solid is cold. Picture ice. So that means the heat left, exothermic, a delta H of less than 0, a delta H that is negative. Okay? And you can also remember some things about intermolecular forces here. We have more intermolecular forces as we get to A because it is holding it in there, better surface tension. And we have more kinetic energy as we go to the right, because we're increasing our temperature. We're going endothermically to the right because we're taking that energy in. We're going exothermically to the left. Doesn't matter if it's jumps or single steps. And that's all.